All right, let's begin. I will begin. Then, Father, we thank you for this day. Thank you for these students. Just ask you to bless our work today, Lord. In your name I pray. Amen. I already hit record. Yeah. Okay, so we're going to be studying field extensions, right? And I already, last time, shared with you the basic idea, which is that to construct E with P of alpha equals to 0 for alpha in E for a given F of alpha equal D for a given f of x in polynomials over f, we use an irreducible factor of f of x. Say f of x equal to p of x times g of x. Then if we construct E as f of x mod the ideal generated by p of x, right? This extension, well, this field anyway, E, serves as a field in which f of x has a 0. In particular, I showed that, we're identifying f with f prime, which is a subfield of E. And in f prime here, I mean, so f prime is equal to C in C in f of x mod p of x. All right, such that, that's not how I want to write it. Uno momento. F prime is C plus p of x, I suppose, such that C is in F. So, I mean, technically speaking, F prime is not equal to F, right? But there's a clear one-to-one correspondence between these two things, right? Like the isomorphism psi from F to F prime is just given by what? Psi of C equals to C plus p of x. Okay. And you can prove that that is in fact an isomorphism. So let's see here. For example, there was more than this, though, right? The what was alpha? Alpha was equal to x plus p of x, and we calculated that f of alpha is equal to 0, right? But even that's, I mean, what do we mean f of alpha? There's something kind of funny going on here, even that, right? What did I do? I mean, technically speaking, what would f of alpha mean? This should mean phi of alpha of f of x, right? This was our f of alpha. This is the evaluation homomorphism. How did we define that before, though? Remember how we defined it? We said things like, well, phi c, or I guess we did phi sub a of f of x was equal to f of a, right? But this was for what? This was for f of x over polynomials over a field. So if you're fussy, you realize that phi a of f of x up there doesn't really make sense because, why? I mean, let's see here. More specifically, this was what? This was a0 plus a1x plus da-da-da plus anx to the n. And then when we take phi a of that, what happens? Bad choice of letters. Oh well. Let me take phi b of that so you can see better. We get a0 plus a1b plus anb to the n, right? But when I looked at the evaluation of the polynomial at alpha, let's see here. So I looked last time, I looked at phi alpha of, a0 plus a1x plus anx to the n. And I said, well, that's, a0 plus a1 alpha plus an alpha to the n. But should that be allowed? I mean, does that? I'm just trying to be fussy here for a second. This is f of x where? And f of x, right? I mean, it's a polynomial with coefficients in the field. But alpha where? Oh, see, this is where I'm being dumb. I think I've forgotten an important thing, which is when we defined phi a, where did we say a had to come from? Did we say it had to come from the same place as the field where the polynomial lives? I don't think we did. So I guess it's okay. Anyway, sorry, I don't think I'm really saying anything at the moment. My apologies. I mean, we could work out again why it is that when we plug in alpha it's 0, but I think that would be a silly use of time. Let me go on here. So let's just look at an example that might be more productive. If I look at, say, f equal to the reals, right? And I look at, let's say, f of x equal to x squared plus 1, then what? Well, in this case, the function, the polynomial is already irreducible over the reals, right? And so if I look at e equal to r of x mod x squared plus 1, right? And then I look at phi alpha of f of x, what do I get? So this is supposed to be, what, alpha squared plus 1. But what does that mean? Let's see here. Alpha, remember alpha was equal to what? Alpha was equal to x plus x squared plus 1. That was what we did in our proof of the theorem. And so what is alpha? This is x plus x squared plus 1 squared. And then here's the thing, is what plus 1? What does that mean, plus 1? What kind of 1 is that? Right. Yes, exactly. That's meaning. So I don't know. You have to be aware of these things if you want to actually flesh out the details, is I'm trying to get at. And I don't think I'm getting there very fast, and apologies about that. So this is x squared plus the principal ideal generated by x squared plus 1 plus 1, parentheses, plus the principal ideal generated by x squared plus 1, which is x squared plus 1 plus the principal ideal generated by x squared plus 1. Ugh. Shut up, you stupid phone. Ah. Huh. That's kind of funny. It's actually a Google story about a news story about the Infinity War. It's kind of appropriate, right? Just my notification sounds also, Avengers. So. So the point is x squared plus 1 absorbs x squared plus 1. And what is this? See, that's 0. This is equal to 0, quote unquote, in E being defined as, the quotient ring by the principal ideal generated by x squared plus 1. What I'm doing at the moment is just working through the proof of the theorem that I just went through at the end of last class and started mangling at the start of this class. Hey, the theorem's true whether or not I can say it, right? It's good. What on earth? My children have too many games on this phone. Hey, stop that. I do not want to play Mighty Micros right now, thank you. Ah, so annoying. All right. I'm going back to my flip phone. Flip phone never did this to me. You know what I mean? Stopped working on the network. There was also that, but there were these stories about a flip phone coming out in Korea in like 2016. And then maybe like they were going to do it there, and then they're going to have like new smart but flip phones in the Americas. But no, there's just stupid tech stories that never amounted to anything. We all have the same stupid phone. It doesn't fold, and it just pocket dials all the time. Why are we suffering this technology? It's garbage. Anyway, sorry. As you can see, in the extension field, x squared plus 1 has a 0, right? Yeah? But my point is, technically speaking, are the real numbers a subset of this? If you want to be fussy, no. But we still say that's an extension field of the reals, with the understanding that we're going to make this identification of cosets with constant representatives in the quotient ring. All right? Enough about that. Let me move on. So, let's see here. Next example. If we have f of x equal to x to the 4th minus 5x squared plus 6. Well, we can factor that. That's x squared minus 2 times x squared minus 3 as it happens, right? So this is reducible over the rationals, right? If we think of this as a rational polynomial, I think that's certainly reasonable. And I said it follows we can form the field q of x mod x squared minus 2, right? So we could look at q adjoin x mod x squared minus 2, right? And so this will be things like, let's say a plus, b, a plus bx. You can put a bar on it if you like. Such that a and b are rational, right? Getting more to the point, we could rewrite this just like this, right? This is really a plus b alpha, such that alpha squared is what? 2, right? And yeah, A and B are rational numbers. So, great. Now, to be fussy, here alpha is equal to what? It's equal to x plus the principal ideal generated by x squared minus 2. All right. We could also look at beta, right? Likewise, we could look at qx mod x squared minus 3, right? And we could look at that as, say, a plus b beta, such that beta squared equals to 3, and a and b are rational. Again, using the construction I've just outlined. And here, beta would actually be, yeah, fine. X plus the principal ideal generated by x squared minus 3. How do I know that x squared minus 2 and x squared minus 3 are irreducible as rational polynomials? Because they don't have a 0. Why don't they have a 0? What are their...
If you try to solve, you get the square root of 2 and square root of 3, which aren't in the function.
Right. So if we know that square root of 2 and square root of 3 are not rational numbers, if you suppose you have a 0, then you would have a square root of... I mean, the 0 is a square root of 2 or a square root of 3, essentially by definition, which we have proved before is not a rational number. Right. Okay. Very good. Alternatively, and much more laboriously, you could look at q mod x squared minus 2 and prove that it's a field. Proving that that's a field would then prove that the thing you divided by was a maximal ideal, and consequently the thing that generates it is irreducible. That seems like a lot more work than what Emily just told me, though, right? All right, so then what? We can, I say, let's look at f of x in q adjoin alpha of x. So what does that mean? So this means polynomials in x with coefficients where? This guy, right? Let's see here. So I would point out that if we look at x squared minus 2 times x squared minus 3, the idea is that we can rewrite that as x minus alpha times x plus alpha times x squared minus 3, I believe. Right? Now, I mean, to be fussy, I should probably multiply that out, right? I mean, it's not clear that it's a polynomial over Q alpha just yet, I guess. How's this work out? We've got x squared minus 2 alpha x plus alpha, minus alpha squared times x squared minus 3, right? Which is what? This is x to the 4th. I'm not sure this really helps us, but, oh, what have I done? Yeah.
X alpha minus X alpha is just 0. Not minus 0.
So here is where the unfortunate thing is that we're using x in two different ways. On the one hand, I was using x to build the alpha, but this x is not that x. To be more pedantic, this, you're like, what? More pedantic? Is that possible? Yes, it is. Check it out. So q adjoin t, mod t squared minus 2. But I get it. I get what you're saying. This is q adjoin alpha, right? Where now alpha is t plus the coset, plus the ideal generator, I mean, technically. So it's this of x. So really here, alpha is equal to t plus this thing. So these are not identically 0 because x is the polynomial which we're building.
Okay, so if you FOIL x minus alpha and x plus alpha, you get x squared, then minus alpha x, and then plus alpha x. So do those go to 0? Yeah, why? You have a minus alpha x plus alpha x that you turned into a minus 2.
Oh, you're asking me something simpler. Well, I'm happy with my response because I feel like I just added something, but it was not what was asked. All right. Oh, look, and somehow it became a cube. Maybe we should just call it a day and like, I don't know. Grief. All right, let me try this. Look, I don't really need to do this, but my point is, it should now be clear, if it wasn't already, that this is a polynomial over q adjoin alpha, right? The coefficients 1, here's the coefficient alpha squared plus 3, right? Which is in q adjoin alpha. And this is, of course, also in q adjoin alpha, right? Of course, if we think of alpha squared as what it is, which is morally what? 2, we're back to what? Minus 5x squared plus 6, not surprising, right? I'm afraid to say this, but you can also look at f of x as being in q adjoin beta. You know, coefficients like that. All right, so let me get to the point, if I'm allowed to do that. I think I'm okay. You guys can see it? All right. I'm just going to stop and count my, not, there's. So the point I'm trying to make, believe it or not, is that there is a field over the rationals in which you can put both alpha and beta, all right? And in that field, right, in Q adjoin alpha and beta, right? So I almost completed my thought here. The point here was that we could write f of x as x minus beta times x plus beta times x squared minus 2. Furthermore, you can also argue, there's more that I could say here than I should say, because it might actually be really helpful for your homework, which is that in this context, I believe you can prove x squared minus 2 is irreducible in this extended context. Suppose it was not irreducible, what would that tell you? If this was not irreducible, it would mean that there's a 0 of x squared minus 2 in q adjoin beta. What would that look like? That in some sense would say you can build the square root of 2 from the square root of 3. And if you get into the details, you'll find a contradiction. If you try to say that, you know, this x squared minus 2 has a 0 inside q adjoin beta, which is the q adjoin. I mean, q adjoin beta, another notation that would be totally reasonable up to isomorphism would be this. Now, if you want me to be fussy, this is only up to isomorphism because technically this is a factor ring where we're forming a factor ring by quotienting by, the principal ideal generated by x squared minus 3, whereas this is a subfield of the real numbers. Well, I'd really like to stop distinguishing between these things and just say that these are equal, as to not go nuts. All right? So anyway, you can prove that x squared minus 2 is in fact irreducible in q adjoin beta. And over here, we could prove, if you wanted to, you could prove that this is irreducible in q adjoin alpha. Hey, let's, all right. But if you look at q adjoin alpha and beta, right, this allows us to factor f of x into x minus alpha times x plus beta times x plus alpha, x minus beta times x plus beta. So we can factor the polynomial into product of linear factors if we have both alpha and beta, because those are essentially what? The square root of 2 and the square root of 3. I mean, no one should really be surprised that we can do this. What I'm trying to explain to you right now is how that happens by a pair of field extensions, one and then another. And you can think about Q. So what this is, this notation here, Q alpha beta, this is the smallest field, smallest extension field of the rationals, which contains both alpha and beta. Right. And most people, when they talk about things, we're working up to an isomorphism. So they would say things like this is equal to Q adjoin square root of 2, square root of 3. And my brackets should be parentheses. All right. What? What? I thought I heard a shouldn't. I just heard something else. You should not confuse me being tired for this material being difficult, by the way. I hope that's not happening. Come on. Wake up, I say. All right. So we need a definition. There's different kinds of numbers in the rational numbers, right? There are some numbers, like square root of, well, they're not even in the rational numbers, right? You're fine. There's some numbers, like the square root of 2 and square root of 3, right? Which appear as zeros to x squared minus 2 or x squared minus 3, right? And so if you can find a polynomial of degree n, which your number is a 0 for, then that's said to be an algebraic number. So here's a more careful definition. Let E be an extension field of a field F. An element alpha in E is called algebraic over F if there exists a non-zero polynomial for which f of alpha is 0, where of course this, has the meaning of the evaluation homomorphism. An element alpha in E, which is not algebraic, is called transcendental over F. All right, so square root of 2, square root of 3, both algebraic over Q, right? Any number in a field is algebraic over that field. If you give me C in a field F, it's algebraic because x minus C has C as a 0, and x minus C is a polynomial in the field. So like square root of 2, square root of 3, they're algebraic in the reals as well. It's kind of stupid, but so what's more interesting, of course, is when we talk about numbers outside of a given field and whether or not those extended numbers are in fact algebraic. So example, this is right here is the stupid comment I just made. The number I in the complex numbers is algebraic over the reals since it is the 0 of x squared plus 1, right? Square root of 2 is algebraic since it's the 0 of x squared minus 2. Oh, here's something more interesting. Square root of 2 is algebraic over Q adjoining the square root of 3 because x squared minus 2 has the square root of 2 as a 0 in this extension field. All right? In fact, if we look at x squared minus d, where d I think has to be, well, if d is square free, it's more interesting, right? Then Q adjoin D could either be a real or complex extension field, and so I guess D could have degree. I don't know whether or not. Well, I haven't even defined degree yet, so let me shut up. Anyway, the point is that if we have the square root of D, it's algebraic over Q. All right, where D is any rational number. Well, excuse me, any integer. This is a bad day, guys. Here's another one. This is a lot like problem what? You guys keep asking me about this one. What problem is problem what? 69, part B, maybe? I there ask you to find the irreducible polynomial for a given number, which is the difference of two radicals. The calculation is much like this. So if I want to show that this number is algebraic, what you want to do is isolate the radical, and then square it to get rid of it, and then isolate the radical again, square it again, and then when you multiply this out, basically replace alpha with x, and then just work it out. This polynomial has alpha as a 0. So this is a simple procedure to produce a polynomial which takes a given number as a 0. Just work backwards, basically. If your number is constructed from a finite series of, like square roots, cube roots, stuff like this, you can work backwards to find a polynomial. However, I should be clear, that does not prove the polynomial is irreducible, right? That will be important because we're about to give a definition. Well, we'll eventually give a definition. There are, of course, numbers like pi and e. Pi or e, these are algebraic over the reals because, of course, x minus pi and x minus e are real polynomials, which take pi and e as zeros, right? Surprise, surprise. But on the other hand, you cannot find a rational polynomial which takes pi or e as a 0. Now, to prove that, that's a lot of work, all right? There's actually a pretty decent proof of e being irrational in the calculus book we were using last, Salas and Hilly at Gen. But anyway, here's the definition. If we have so what's algebraic and what's not depends on the base field. So by default, number theorists like to take what as the base field? Rationals, right? So we say x in the complex numbers is algebraic over q, then we say it's an algebraic number. And x in the complex numbers, which is not algebraic over q, is known as a transcendental number. This is the standard usage of the term outside of this course, right? The base field is taken to be the rationals. The extension field is taken to be complex. And with a theorem, it says that if E is an extension field of F and alpha is an E, then alpha is transcendental over F if and only if the evaluation homomorphism gives an isomorphism of polynomials over the field with a subdomain of E. And here's the evaluation map. It's this, right? And it's simple enough to prove that this is a homomorphism, all right? And great, so it's a homomorphism. This phi alpha is a homomorphism from polynomials to the extension field E, right? What would it take for it to be injective? It means that this maps to 0 only if what? If we map this to 0, then that must be 0, right? What if this was equal to 0 for something non-zero? What would that say about A1 through A0? A0 and A1, AN. Well, that would define a polynomial. That would actually define a polynomial. If you could find this equal to 0 for some set of non-zero A1 through A0, AN through A0, then that would mean that alpha is algebraic, because it would be a polynomial equation which alpha satisfied. So if alpha is transcendental, the kernel must be 0, which means that phi alpha must be injective, which means that it's an isomorphism onto its range, right? In the converse direction, if it's injective, the kernel 0, which says that alpha is not algebraic. So that's kind of neat. Essentially what it says is that if you work with a transcendental number over the rationals, it's like working with polynomials. So q adjoin pi, where is it? Well, this is the field. So q square bracket pi would be polynomials in pi, like rational coefficient powers of pi, finitely many, non-zero. This is the field formed by adjoining pi, which is essentially rational functions in pi. Anyway, let's go on past that. I don't really have much more to say about transcendentals that won't confuse you and me at the moment. So this theorem is somewhat important. It lays the bedrock for a bunch of calculations we do, and here it is. So E is an extension field of F, alpha in E, such that alpha is algebraic over F, then there exists an irreducible polynomial P of X over the field for which P of alpha is equal to 0. Moreover, P of x is unique up to a multiplicative constant in f. It is unique up to a multiplicative constant polynomial of least degree for which P of alpha is equal to 0. Furthermore, if you have f of alpha is equal to 0, then it must be that P of x divides f of x. So what this is saying is that, we've been finding these polynomials which take the square root of 2 or I as a 0, right? It's saying that there exists a polynomial of smallest degree which is unique up to a multiplication by a unit, right? So we might as well make the polynomial monic, which means monic polynomial has leading coefficient of 1. If we insist on using a monic polynomial of least degree, which makes it 0, then that will be the so-called irreducible polynomial of the number. So this proof is one I will skip. And this is the definition, but you should work through that proof. It's not bad. E is an extension field of f, and suppose alpha is algebraic over f. The unique monic polynomial of least degree for which P of alpha is equal to 0 is known as the irreducible polynomial for alpha over f. And here's notation for it. Alpha f equal to P of x. The degree of alpha over f is the degree of the irreducible polynomial. So I was arguing with you that x squared minus 2 and x squared minus 3 were polynomials of least degree, which take square root of 2 or square root of 3 as their 0, right? That shows you that square root of 2 and square root of 3 are degree 2 because they're irreducible polynomials, namely x squared minus 2 and x squared minus 3 have degree 2, all right? The imaginary number I is degree 2 over the reals, right? It's also degree 2 over the rationals for what it's worth, right? Because x squared plus 1 is the irreducible polynomial of I. See if I have anything more interesting. The fifth root of 2 is a 0 of x to the fifth minus 2. How do I know that that's irreducible? Thank you, Eisenstein. So this is irreducible by Eisenstein's criteria, which shows you that the fifth root of 2 is degree 5 because its irreducible polynomial is x to the fifth minus 2. We love Eisenstein when it works. I don't think Eisenstein is going to help you on part B of that homework problem, though. More on that in the help session. Let's see here. We say a field E is a simple extension of F if E is an extension field of F, which you can look at as F adjoined a single element alpha, right? So we also define F alpha as the smallest subfield which contains F and alpha. Similarly, F alpha adjoined alpha n is the smallest field which contains F and all of these 1 through n. All right. Yet another theorem. So here, I say E is a simple extension. If E is a simple extension F alpha, all right, of a field F, and this is for alpha algebraic with degree n, then for each beta in E, there exist these n unique constants, beta 0 through beta n minus 1, for which beta is equal to a linear combination of a constant and then powers of alpha up to n minus 1. So what is this saying? I mean, if you really look at what this theorem is saying, it's saying that if you have a simple extension by a degree n element, what you're looking at is something that is a vector space of degree n over the base field, with basis 1, alpha, alpha squared, alpha cubed, alpha to the n minus 1. How do I know that? Well, I said there exist unique coefficients, right? So the unique existence of these coefficients, if I set this equal to 0, right, then that forces the 0 combination to make each one of these coefficients 0, which is to imply linear independence over the base field of the constant alpha, alpha squared, alpha to the n minus 1. All All right, so what I'm saying is that if you look at a degree 2 number and you extend over the base field, you've got a 2-dimensional vector space. Like Q adjoint square root of 2 is a 2-dimensional vector space over the rationals. Or how about this? R adjoint I is a 2-dimensional vector space over the reals. Complex numbers are a 2-dimensional vector space over the real numbers, right? If we were to look at Q adjoin this with a 5th root of 2, that would be a 5-dimensional rational vector space. And the proof here, what is it? We take the irreducible polynomial which defines alpha as its 0, right? We know that P of alpha is equal to 0, which means that alpha to the n is equal to all this, right? And I call that star. And I said the smallest field containing alpha and f is given by the quotient f of x mod p of x. We know that this is a field because p of x is assumed to be irreducible, which means it's maximal, which means this quotient's a field, right? And so setting alpha equal to x plus the ideal generated by p of x, this E has elements of the form this. Now I put m here because I don't want to assume the result. But m could be some natural number, and we can use this star to reduce any expression with m larger than n as follows. All right. What I do is I show how to. Let's see. I suppose inductively there exists Cj for which alpha to the m is equal to that for some m greater than or equal to n, and then I look at alpha m plus 1. Well, what's alpha m plus 1? So I'm going to do it by induction on m. So alpha m plus 1 would be alpha times alpha to the m, but I'm assuming that this allows a reduction into up to the n minus 1 reduction like so. So I put that in there, and then that gives me what? The highest order term in here gives me alpha to the n, and then I have lower order terms from 0 to n minus 1. But the cool thing is alpha to the n, I already know I can reduce back using star again, like so. And then what do I have? I have something of degree n minus 1. So again, alpha to the m plus 1 is reducible to something that's a linear combination of alpha, powers of alpha up to n minus 1, which proves the induction step. Therefore, we can reduce anything of this form to just powers of alpha up to n. This is intuitively obvious, right? If you have alpha to the n is reduced to things less than n, then of course anything that's higher power than n you can reduce down using that star equation. Like this induction is not surprising. And then I prove uniqueness, yeah? So to prove uniqueness, suppose that there exist 2 pairs of constants like so and like so, right? Set them equal and define g of x to be, you know, the difference of these, like b0 prime minus b0, b1 prime minus b1, and so forth and so on. What do you got? You got a polynomial of degree n minus 1, and by construction, if you look at this polynomial, right, if you plug in alpha, what do you get? See, if you look at the equation above and the construction is polynomial, if we plug in alpha, we get 0. So this would be a non-zero polynomial of degree less than n, which takes alpha as a 0. This is forbidden, right? Which the only way that can be the only way that this polynomial would not be the 0 polynomial is what? If in fact all of these coefficients are in fact just 0. Which is precisely what we need for uniqueness of the decomposition into powers of constants through alpha n minus 1. And so there you have it. We have that 1 alpha all the way out to alpha n minus 1 is a basis. It's a basis for the extension, the simple extension by alpha. And so I already said this, but this is the corollary, just sealing the deal. If we have a simple extension by alpha, then we've got a vector space of dimension n over the base field, right? So anyway, the next section is actually rather short, but I'll talk about the details of that Monday. I think you can do the homework without, well, I don't know. I'll try to help you with the homework in the help session today. But anyway, we can stop here for now.